All right, here we go with lesson 1.3, part 1. A couple properties that you're going to see on here that we're going to be using. All of this is found on page 76 of your chapter 1 book, so you can always take a look at these. No need to necessarily rewrite all this if you don't have these notes printed, but a couple basics real quick that we'll just throw out there. The limit as you approach any value of b, so this would be more like a constant like you're seeing over here. So here's like a real number example. As x approaches any value, my answer would simply be this. So if you think of the equation y equals 5, well, no matter what value for x I have on that line, my y value is always going to be 5. So if I plug any number into that function, right, it's always going to be 5 is the number I'm approaching. So if you had the limit of, here's the function y equals x, well, if I plug any number in for x, right, so as x approaches any value, I'm going to get that value. So if I was looking at the line y equals x, well, if I plug in a 3 for x, right, so as x approaches 3, so if I sub in a 3 for x, I get 3 as my result. Every point on this line of y equals x is a duplicate value. Like this would contain the point 1, 1, 2, 2, 3, 3, 4, 4, on and on and on. So you would always get this as your answer. No matter what you plug in for x, you're going to get that value. If you have an exponent involved, it's real similar to this. No matter what I have, if I plug in this number for x, then it would be that number to whatever this exponent is. So if I had x squared, as x is approaching 3, if I sub in a 3 for x, then I would have 3 squared, and that would be our limit. So a lot of this today now in this section is going to be based on just direct substitution, which is a real simple way of getting a limit when it's available. It's not always available. We'll take a look at that, but when it is available, then we can use it. So direct substitution, so the limit of any function as x approaches a value is simply that y coordinate, so f of c. So if I'm plugging in c in for x, it creates a y value, and that's what this is saying. So, but that's only true as long as the function is continuous at c, meaning you don't have any holes or asymptotes at that value, and it's actually defined at that value. So in other words, you can actually plug in a number and get an answer. We saw ones in the previous lesson where there are certain numbers you cannot plug in. So like this one right here, for example. So we'll get to that in just a second. So as you look at our first example, so the limit of this function as x approaches 2, you'll notice on this one is clear for direct substitution. We know this would just be a positive parabola if we graphed it. And obviously there's no limitation on plugging in a 2 for x because it's not like it creates a 0 denominator or something like that that would keep us from being able to do that. So we could simply plug in a 2 for x, and that's what you're seeing right here, and that result. So that would be our limit, since we can just directly sub that in. Let me go down a little onto this one. So here's a case where you can see I cannot use direct substitution because the limit as x approaches 1 is undefined at 1. So if I were to plug in a 1 here, it creates that 0 denominator, so it's not possible with direct substitution. Just because it's not possible with direct substitution doesn't mean there's not a limit. It just means I would have to take a different approach. So I might need to look at the graph, or I might need to make a table and figure out my answer that way. Let me show you from the table first. This is what we did in our previous lesson. So on this one, I have to take a look at, since I can't do a direct substitution with 1, I have to look at what is my y value becoming as I approach 1 from the left, and what is it becoming as I approach 1 from the right. So right here you can see these are the y values if I approach 1 from the left. So if I came at it from 0.9, 0.99, so I'm getting closer and closer and closer to a value of 1 from the left, and these are the y values that you're seeing. So you can see on this one, these are simply getting exponentially bigger in these cases. It's just becoming larger and larger and larger, or I should say smaller, because it's becoming a bigger and bigger negative. So you can see that this is technically approaching negative infinity because I'm just getting bigger and bigger negative values. If you approach 1 from the right, so 1.1, 1.01, 1.001. So now I'm getting closer and closer to a value of 1 from the right side. You can see these are just getting bigger and bigger. So these are approaching positive infinity. So since I'm approaching negative infinity from one side, positive infinity from the other, this would just be a limit that does not exist. So we could figure that out from making a table. We could also figure this out by looking at the graph. So I'll show you that graph here real quick. So if you were to graph it, it would look like this. So the limit as x approaches 1. So here's my limit, here's my value of 1. So look at this line right here. So you can see that would be a vertical asymptote running right through that guy right there. But just because it doesn't exist for a value of 1 doesn't mean you can't get a limit. So f of 1 does not exist, but we can still potentially get a limit as x approaches 1. So as I approach 1 from the left, you can see by this graph it's just going to continue going down and down forever. So that's why the left side approaches negative infinity, and that's what we were seeing right here as those numbers become larger negatives. As you approach 1 from the right side, you can see it's going to go up and up and up forever. And so that's why from the right side it's approaching positive infinity. Right? And so in a case like that, we can tell by the graph and from these tables that the limit does not exist. And again, don't forget, when you're approaching, even if these were in agreement, let's just say they were both positive infinity, it would still not exist, right? The limit does not exist if you're approaching infinity. So we said before that, you know, in calculus next year, your teacher might say, well, if you approach it from one side, you can say that it approaches negative infinity, but that's not really the limit. That just describes what the graph is doing, right? It just describes that it's going downward forever as you get closer to this number from the left side. So jump over to example 3 here. So on this one, you can see this one is a good candidate for direct substitution because I can simply plug in a 1 and it doesn't give me any issues like a 0 denominator or something like that. So in this case, we could just go ahead and plug in a 1 right there, and then we just got some cleanup to do. So I have e to the first times the sine of 3 pi over 2. So we know the sine of 3 pi over 2 is negative 1. So negative 1 times e is simply negative e. So direct substitution is a great way to go as long as the function is defined at that value. All right, let me go down to one last one here. So I wanted to show you on this one, there are going to be some cases where direct substitution may not work initially, but if you simplify it, then you may have a situation where direct substitution does work. So if you looked at this one, if I looked at it initially from this point, I cannot sub in negative 3 right here because it creates my 0 denominator. But if you factor the top, so this is a sum of cubes, this is what that would look like if we factor that out. So that's something we did earlier in the year. But you can see now how these factors would cancel, and this is what I would be left with. Quick reminder on these guys. If these did not cancel, let's just say this was anything else like x plus 6. If these did not cancel, then this creates an asymptote in the graph. This is where vertical asymptotes would come from. If they do cancel, then instead of an asymptote, you now have a hole in the graph at that point. So because these do cancel, we have a hole in the graph at negative 3. And so we can see that in the initial graph, it wouldn't work. But once you simplify it, now I can do direct substitution because now in this version of the setup, negative 3 does exist. So now I could plug in negative 3 in order to get my limit. So if you do see a case where direct substitution doesn't work initially, see if you can simplify it, and then maybe direct substitution would be an option from there. Again, if direct substitution is not an option, your other two methods are what we looked at here. I can always do a little table and see what values we're approaching from the left side and from the right side of that value. Or I can, if it's available, I can look at the graph and see what I'm approaching from the left and from the right as I look at the graph. So that's all we got for part 1 here.